In this session, I will be explaining how to solve the focused questions for the grade 12 ASP. Let's first begin with the term 1 materials. Which of the following pairs cannot be mixed together to form a buffer solution? Before I answer, I'm just going to give you the options of how to form a buffer solution. There are many ways to form a buffer solution. First way is to mix a weak acid with its conjugate base, with its own conjugate base. Like for example, HF, I'm mixing it with F minus. Or mix a weak base with its own conjugate acid. Like for example, if I have NH3, I'm mixing it with NH4 plus. These are two ways. Or you can also add a strong acid with a weak base. Like for example, I'm just gonna erase this option so I can write. So the option number 3 is to mix a strong acid with any weak base, like for example HCl plus NH3, that's an option. Or mix a strong base with a weak acid, like for example NaOH and HF. So these are the ways to form a buffer. Now let's look at the options given to us in order to select the two pairs that cannot make a buffer. So here we go, HONH2 and HONH3. So here we go. In this one, I have an acid and a base. So here you can look at the difference in the hydrogens in this one. So that's the base and that's the conjugate acid. Cl is just a spectator ion, so you can ignore it. Now HONH2, it's a weak base. So that's a buffer. I cannot take this option. Now that's a salt, NaCl, a neutral salt, and that's a strong acid. So neutral salt plus a strong acid. So that's not an option to form a buffer solution. And this one, that's a weak acid and its own conjugate base, F minus. So here we have HF and F minus. Na is just a counter ion to couple the F, just a spectator ion. It's a neutral, pH neutral ion. And again here, NO2 minus and HNO2. That's an acid with its own conjugate base. So when you want to look for an acids and their conjugate base, or base and their conjugate acids, just count the difference in hydrogens between the two formulas. Like for example here, I have in this one 3 hydrogens, I have 2, so these are conjugates. This is a strong acid, so that's not an option. That's not a way to form a buffer. Here I have a weak acid with HF. Here there's no hydrogen. Here there's no hydrogen. Here there's a hydrogen. So that's a good way in order to know whether the compounds given to you are conjugates or not. Let's move on to a different question. So, which of the following pairs, again, cannot be mixed together to form a buffer solution? So as I told you, let's follow the technique of counting hydrogens. NH3 and NH4. That's a weak base with its own conjugate acid. So that's a buffer. And specifically, that's a basic buffer. So here we want us to choose the couple that cannot make a buffer. So this one makes a buffer. Now let's look at this one. C2H3O2, C2H3O2 minus. Look at this minus. This one should supposed to be here. Now this is a counter ion. So basically this and this are the same substance of weak base. So that's not a way to form a buffer. I cannot mix a weak base with another, with itself. Now, looking at the other option, that's a strong base mixed with a strong acid. Strong acid. And here, this is also an option that a compound cannot, this is an option, I cannot make a buffer by strong acid and strong base. And the last one, weak acid and its own conjugate F minus. Look, there's HF and KF. So here in this one, basically, there are two answers, but I think that this one, there's a mistake in writing the formula, so it should be given in a different way, probably like this: C2H3O2 with an A and C2H3O2H. This is how it should be given to be correct, so that I can only choose option C as a correct answer, because this is a weak acid and its own conjugate base. Now, moving on, a solution containing which of the following pairs will be an acidic buffer? To have an acidic buffer, I need a strong acid with a weak base, or I need a weak acid with its own conjugate base. So let's look at the options given here: strong acid and neutral salt. Not an option. The next one, strong acid, again with a neutral salt. Wrong. Again, C, same thing. But when we reach D, I have a weak acid with its own conjugate base, F minus. So that is an acidic buffer. Defining a buffer solution. A buffer solution is a solution that can resist the change of pH whenever a small amount of a strong base added or a small amount of a strong acid added. So I'm going to write this as a substance that resists the change in pH upon adding a small amount. Of course, we're not talking about a large volume of acid added or base added. It's just a few milliliters. A small amount of a strong acid. So if a strong acid is added to the buffer will slightly have a drop in its pH, or so adding a small amount of strong acid or a small amount of a strong base. So if a strong base is added, a small amount of a strong base is added to a buffer solution, the pH of the buffer will slightly increase. So the buffer is responsible that the pH doesn't increase or decrease a lot. Now, I must also mention that a buffer solution should contain either a weak acid with its conjugate base, or a weak base with its conjugate acid, or a strong acid with a weak base, or a strong base with a weak acid. Now, let's give an example of an acidic and basic buffer. So, of an acidic, the most common example is HF. It's a weak acid with F minus, or you can write it like this: HF with NaF, so that you don't put an ion, you leave F with a counter ion. That's acidic. Now, basic buffer, I have NH3 with NH4 plus, or you can say NH3 with NH4Cl, for example. Another example of an acidic buffer, well known, CH3COH, that's an acetic acid with acetate, CH3COO minus. Moving on to calculations. What is the pH of a solution prepared by dissolving 0.0 mole of acetic acid? Think that's a weak acid, and I'm mixing it with 0.3 mole of sodium acetate. So I'm mixing a weak acid with its own conjugate base. So we're dealing here with a buffer. In water sufficient for 1 liter solution. Of course, we need the volume of this solution, because in finding the pH, when we use the Hazel-Bulk equation, we need the concentration of acids and bases and not their mole. And the concentration, which is the molarity, is the mole per liter. It's the mole per liter of a solution. So here we can say that the acetic acid, I'm going to use it as HA. Concentration is 0.150 over 1, 0.150 molar. And the concentration of its own conjugate base, which is the acetate, is 0.300 over 1, 0.300 molar. So now I've calculated the molarities of the acid and its own conjugate. I need to apply the Hazel-Bulk equation in order to calculate the pH of that acid, of that buffer. Always use the formulas given in your formula sheet. The Hazel-Bulk equation is pH equal pKa plus log the base, the conjugate base, over the acid itself. Now, note here that we need to use the pKa, but again, I'll tell you in the formula sheet, you have how to calculate, how to get the Ka from the pKa. And it is, so Ka is, I'll just put the formula in its easy way. pKa equal minus log Ka. So you're going to plug over here 1.8 times 10 to the power negative 5. And you're going to put it in your calculator and you will get the pKa. So in this case here we have minus log of 1.8 times 10 negative 5. That's a 4.74. So 4. So pH equal 4.74 plus log the base, the conjugate base, which is this one, over the acid. So 0.3 over 0.15, log the answer. And the final answer is 5.04. The pH has no unit. Moving on. In a buffer solution, when the concentration of a weak acid and its conjugate base are equal. Okay, let's see what does that mean. That's the Henderson equation. pKa plus log A minus over HA. So they are saying when the concentration of this is equal to this one, we're talking about log 1. So pH equal pKa plus log 1. If you do log 1 in your calculator, that is equal to 0. Therefore, pH will be equal to pKa. And we call this the half equivalence point, by the way, on the titration curve. Moving on, which of the following have the greatest buffering capacity? The greatest buffering capacity is the buffer, is the buffer that resists the most the changes in the pH. So whatever you do, adding a small amount of strong base or small amount of strong acid, the pH of a buffer has to maintain its value and not increase or decrease a lot. And this will show the capacity and the effectiveness of this buffer. And again, this is all related to the quantities of A minus, the concentrations of A minus and H plus. So again, if you look at this formula, if they are equal, we are talking about a buffer that is equal to the pKa and almost doesn't change. That's the best buffering capacity when the concentrations are equal. 1. So the concentrations are equal. And second, when the concentration are high. Like for example, I'll give you an example. If I have 0.01 molar and 0.01 molar acids and its own conjugate base, it's not as good as if I have, for example, 0.1 molar and 0.1 molar weak acid. So having equal concentrations is good, but having them higher is even much better for the effectiveness and capacity of the buffer. So therefore, we look at the options where we have equal amounts. Here almost equal, but this one is equal amounts and higher. You remember that question that I told you about C2H3O2? Look, here's the hydrogen. And this one is without H at the beginning. It's replaced with an A. In that example, I wrote the H on the side. It's the same, okay? So this is another proof that this is a buffer. Now, let's continue. What is the range over which a buffer will be most effective? So when I look at this formula, when it is most effective, again, it is effective when the pH equal pKa, and that is when the H, then the A minus, is equal to the HA. So when they are about the same, the closer they are to each other, the better the effectiveness of the buffer. Now let's continue. Titration curves, define equivalence point and endpoint. There's a big difference between equivalence and endpoint. Endpoint means when you stop the titration. Equivalence is coming from the word equal, so there must be something equal in here. So let me first explain. Define equivalence point is when the moles of acid are equal to the moles of the base added. So at that point, when we have equivalence point, we say NH plus equal NaOH minus, which gives us the excuse to use this formula, CAVA equals CBVB, so that we can calculate the concentration of the analyte. Now, end point. When we are doing the titration, our eyes are not a microscope. We are not able to observe and see when the mole of the acid becomes equal to the mole of the base. Therefore, we have the help of the indicator. And the indicator at the equivalence point will not switch color. It's not going to give you a color indicating whether there's an acid or there's a base. The indicator will switch color when the acid becomes slightly more than the base or vice versa. So the end point is when the color of the indicator changes when we are doing changes during the titration. During the titration. At that point, we know that we should stop because the titration ended. We reached the equivalence point. Moving on to labeling graphs. I am expecting to get questions in the exam where you have to label graphs. So first, let me start studying this graph. There are main important points on the graph that you need to pay attention to. Like from which point the graph is starting, what is the pH at the equivalence point. So here's a curve starting from below going up. So as a start, this is the titration of an acid with a base. Now, next, here the pH starts with initially below 2, and there is a slight increase in the curve. There is no jump like that in the curve, which means that This is the titration of a strong acid with a base. Now, moving on to the equivalence point. The equivalence point, the pH at equivalence point, when it is equal to 7, then I'll know that I have a titration of a strong acid with a strong base. Now, let's start. Here I can label this that this is the pH of the analyte at the beginning of the titration. We did not yet add the titrant. Okay? Now, here this is the increase of the pH during the titration. We just yet did not reach the equivalence point. And at this point, more H plus than OH minus are available. Okay? Because we're still here. This is the titration. So here's the conical flask. Here I'm adding the strong acid. And here I am adding the titrant. So the titrant here, I must say, is the strong base, which in this case, an AOH. So first, at this point, we are still in a medium that is acidic. That's why I'm saying H plus is more than the OH minus. At that point, that is called the equivalence point. This is the equivalence, the pH at equivalence, and this is the volume at equivalence. And whatever comes after the equivalence point is, I call it after equivalence point. It is when now I have more OH minus than H plus. Now let's continue with another example of a titration curve. Here we have a titration of a bi. So let me start. This curve starts from up and goes down. So it means I am titrating a base by an acid. Now, here, the acid, the titrant, always you can get the nature of the titrant from the x-axis. The titrant is a strong acid. Now I just need to check if the base titrated is a strong or weak. Let's look at the pH at equivalence point. It is not 7. So we have a weak base and not a strong base. That's one. Second, look from where the curve is starting, from below 12. It means this is indicating a weak base. This is the pH initially. pH of the analyte at the beginning. Also, there's a slight drop. There's a drop in the curve. Look here, we didn't have an increase in the curve. Here we have a drop. The curve didn't start like this and then decreased. So this is another indication that we have a weak base. And the pH at equivalence point is less than 7. Now here they're telling you because NH4 plus is present, which is hydrolyzed. I'm just going to explain this briefly. At equivalence point, I have here a weak base titrated with a strong acid. At equivalence point, the mole of NH3 used is equal to the mole of HCl used. Therefore, we reach equivalence point. However, when we write the equation, it's NH3 reacting with HCl to give NH4 plus and Cl minus. This is a pH neutral ion, but this one is a weak acid. That's an acid that's going to hydrolyze with water to give me more H3O plus. So an H4 plus, since it is present at the equivalence point, it's going to react with the water present and hydrolyze and give me H3O plus, which explains the nature of the acidity of the medium at equivalence point. This explains why the medium is less than 7 at equivalence point. Now let's move on to another graph. here I have a weak acid with a strong base. Look at the curve, there's a slight jump. It's not starting from here with a slight increase, there's a slight jump. So this is the pH initially, showing that I have a weak acid as an analyte. This is before equivalence point. This is the buffer range. This is before the equivalence point when the mole of the weak acid are more than the strong base. So, or we can simply say that's the pH buffer range. So much better. Here we can use the formula of pKa plus log A minus over HA and know the quantities of A minus and HA. Next, here's the equivalence point. But in this case, since we have a weak acid with a strong base, we're titrating it. So the pH at this equivalence must be above 7 because, let me give you an example. Here's a weak acid. Here's a strong base. At equivalence point, these are equal. So when they react together, I have F minus that is going to result from HF. Okay, so it's like that. I'm gonna write it. So NaOH plus HF, I'm gonna get NaF and H2O. Now look at NaF. F minus is a weak base, Na plus is a neutral, pH neutral. So this F minus again is going to react with water and will hydrolyze to give you HF and OH minus. The presence of OH minus at the equivalence point is the one explaining why the pH is above 7. And here, this is the point after equivalence point when the base or the OH minus is more than the H plus present. Again, titration of a polyprotic acid. We have diprotic, meaning it contains 2 protons, and we have triprotic acids. Now you need to count how many equivalence points you have. So that's the first equivalence point, that's the second equivalence point. Therefore, the curve represents the titration of a 25 milliliter of a 0.1 molar of a diprotic acid with a base. Now, it's always with with a strong, let's take it with a strong base. It could be any strong base like LiOH, KOH, NaOH. Again, here this curve represents the titration of what? 1, 2, 3 equivalence points. So in this case, I have a triprotic acid. Diprotic and triprotic are all weak acids except H2SO4. So let's take it with a strong base. And next, what is the concentration of 100 milliliter? So I'm looking for a concentration of 100 milliliter of an acid. So I'm looking for the concentration of acid, knowing the volume of the acid when it's titrated with 25 milliliter of 0.5 molar base. So here, since we have here CaVb. So we can say that at equivalence point, the mole of the acid are equal to the mole of the base. Therefore, I can write CaVa equals CbVb. Therefore, it is times 100 equals 0.5 times 25. And the final answer, the concentration of the acid, 0.125 molar. Note that we don't need to convert the volume into liter since both of them are in milliliter. We now reach the material of term 2. Describe the relationship between delta G, the standard Gibbs free energy, the standard cell potential, and K. So these relationships are given in your formula sheet. I'm just going to give you the formulas and just some notes with it. Delta G, the Gibbs free energy, is minus NFE cell. If you are doing a question where you need to use this formula, you have to remember that when you're done, you need to divide by 1000 in order to get the answer of delta G in kilojoule per mole and not in joules per mole. Now, N represents the amount of mole of electrons transferred. F is a Faraday constant, and E cell is the potential of the cell, the battery in which the reaction took place. Now, there's another formula for the delta G, which is also linking the R with the K, the equilibrium constant of a reaction. So minus RT link K. Again, if you are using this formula in calculations, again, you must not forget to divide this by 1000 so that you can get the delta G in kilojoule. Now, R is a constant given to you, and T is the temperature at which the question is solved. Most probably in the standard cases, it would be at 273 Kelvin. And there's also, if I take this formula and I put it next to this formula, I'll get minus NF E cell equal minus RT ln K. Now, removing the minuses from each side, they can cancel out. I can say that E cell is equal to RT over NF, that's all of it a constant, ln K. Or there's another formula that I taught you in class, which is E cell is equal to 0.0592 over N log K instead of ln K. So when you are solving a question and you have to find E cell by using the given value of K, you can use either this formula or this one. They will both give you the same answer. Identify the relationship between delta E cell standard and Gibbs free energy standard and K, specifying the sign of each. If the equilibrium constant K of a redox is less than 1, K is less than 1. Here we are dealing with a non-spontaneous reaction, a reaction that doesn't want to proceed forward. At this point, the delta G standard is going to be positive, more than 0, and E cell is going to be negative. Okay, now moving on, if the equilibrium constant K is greater than 1, here we are talking about a spontaneous reaction. Of course, the delta G is going to be a negative value, less than 0, and the E cell will be a positive potential. So this is less, this is more, this is like that, okay? Now, if equilibrium constant is equal to 1, at this point, the E cell is 0, and delta G is at equilibrium. We say that the cell is at equilibrium. The equation used to calculate E cell from delta G standard and identify what N and F stands for. So again, you have to go to your formula sheet, and I'm talking about this formula. So delta G is equal to minus NFE cell. That's how it's written in your formula sheet. N stands for the amount of electrons transferred. So during the in the battery, so usually the unit of N here is mole of electrons, and F is the Faraday constant, which is a given value, a constant that is equal to 96485 coulomb per mole electron. So that's why they can cancel out. And E cell is in volt, the voltage of the battery. Now, the next question, write the equation used to calculate E cell from K. So as I mentioned earlier, delta G is equal to minus NF E cell and also equal to minus RT ln K. So if I put these two formulas next to each other, I'm going to get E cell is equal to R constant, T temperature in Kelvin, N moles of electrons transferred, F Faraday constant, and ln K, K is the equilibrium constant. Now let's see how we use these formulas. Calculate delta G in joules. Usually we calculate delta G in kilojoules. Here they are telling us get it in joules. I'll explain to you why. For the reaction of zinc and 2Ag plus, Zn2 plus, and Ag given the E cell. So we are going to deal with this formula. Didn't here I mentioned that you need to divide by 1000? That is because you need to get the delta G in kilojoule per mole. Now, since in this question they are helping us and they are telling us find it in joule, so I'm not going to divide. So delta G equal minus NF E cell. How do I look at the electrons transferred? Just take one here. Zn to Zn2 plus, that needs electrons. Or you can simply take 2Ag plus to 2Ag, that also need 2 pluses, 2 electrons. So the N here is equal to 2. F is the Faraday constant. You will get it from your formula sheet, and E is given to us. So when I get the answer, I'm gonna find it to be equal to negative 22847.6 joules. This is a standard, so it has to be joule per mole. Now, if I divide it by 1000, my answer is going to be minus 22.847 kilojoule per mole. Please be careful to the units. Moving on, which type of reactions are driven by electrolysis? Electrolysis is a reaction that uses battery or a power source to drive or to for a non-spontaneous reaction to happen. So use a power source to convert electrical energy into chemical energy. So basically we have a reaction that's not going to happen, a non-spontaneous reaction. Now this non-spontaneous reaction, if we provide it with the outside intervention like a power source, a battery, this non-spontaneous will happen, will take place. So here, which type of reaction are driven by electrolysis? Non-spontaneous reactions. Explain why an external source is needed. Because this reaction, for example, the hydrolysis of water, H2O that is liquid, there's no way the H2O can give you oxygen gas and hydrogen gas just like that by looking at it. So in order for water to decompose into those two gases, we need to interfere. This is a non-spontaneous reaction. And how do we do this? With the use of electricity. So with electrolysis, the decomposition of water becomes possible. So, which means require the use of a battery. Explain using diagram the difference between voltaic cell and electrolytic cell. I'm going to draw a galvanic cell and voltaic cell. Now in both of them I have electrodes. Okay, and here I have an electrode and I have another electrode, and these electrodes are connected together. So again, these electrodes are, let me just lower it a little bit. So these electrodes are connected together with a wire. Now here there's a voltmeter, here there's a battery source. So this is the positive side, meaning that that's the anode, the positive electrode, and this is the negative side, meaning that that's the cathode, the negative electrode. Whereas in the, so that's electrolytic and that's voltaic. Whereas in the voltaic, the anode is the negative electrode and the cathode is the positive electrode. Okay, so that's the first difference. Here in the, I have a salt bridge connecting these two half cells. In the anode now, there are some common things. I'm not going to mention it. I'm just going to highlight the differences. So in the voltaic cell, it is a spontaneous reaction occurring in which a chemical reaction that takes place, and it converts chemical energy into electrical energy. Because after the chemical reaction proceed, which is the result of oxidation and reduction, a current is created, and we can measure the voltages of this battery with a voltmeter. Here, it's a non-spontaneous reaction taking place that requires a power source, requires a battery. Okay, so we need an external voltage source, whereas in here, in the voltaic, we don't need an external voltage source. The rest are basically the same. I have an oxidation at the anode, I have a reduction at the cathode. Electrons, they move from anode to cathode in both, current from cathode to anode, etc. Which one contains a salt bridge? The voltaic cell, and the salt bridge maintain the battery neutrality, the balance of the charges in the half cell. And the electrons of the salt bridge goes as follow. The negative ions in the salt bridge, they migrate towards the anode, and the positive ions of the salt bridge, they migrate towards the cathode. In both, electrons always flow from anode to cathode, and the current is the opposite. Which one requires a battery? The electrolytic requires a power source. Moving on. Now, what is the electrolysis of aqueous LiBr? What are the products at the cathode and at the anode? Molten. When they say molten, so we should not think about H plus and OH minus ions that are present in water. Simply, we look at the compound given to us, KBr. This is the ion that is going to be discharged at the cathode. K plus is going to be discharged at the cathode, giving K, metal, that is liquid at the cathode. And Br minus is the anion that's going to be discharged at the anode. And it's going to give me Br2 with 2 electrons that is given at the anode. So at the cathode we obtain metal K, at the anode we obtain liquid bromine. Predict the product of electrolysis of aqueous. Now when we talk about aqueous, we have to take into consideration the ions coming from water. So we have a competition at the cathode. At the cathode, I probably have H plus that might be discharged or Li plus that I have to think about. And at the anode, I have the ion coming from the water or the bromide ion coming from the compound itself. So which ions will be discharged? Now, since this belongs to group 1, it's not going to be discharged, and therefore H plus will be discharged. And at the cathode, the product obtained is hydrogen. H2 is going to turn into hydrogen gas. Now at the anode, since Br is a halogen, belong to group 17, and there are 3 options, either Cl or Br minus or I minus. If those ions are present, then in this case, it's the ion itself discharged at the anode, and Br minus will give me Br2 liquid bromine gas, gas, I keep saying liquid, bromine gas at the anode. If you have a difficulty understanding the electrolysis of molten and aqueous, just check the video tutorial of electrolysis down in the description. Write the oxidation reaction at the anode and cathode for the electrolysis of aqueous. Again, at the cathode and at the anode, Li belongs to group 1. So Li plus will not be discharged at the cathode. It's the H plus that is going to be discharged at the cathode, plus 2 electrons. So here, again, I repeat, there's a detailed explanation about the products of electrolysis in my video tutorial. At the anode, it's a Cl minus, so OH minus is not discharged here. Li plus is not discharged here. It's the Cl minus that is going to give me the Cl2 gas. So that's a gas and that's a gas. In the answer key, you will find the answer written 2H2O giving H2 and 2OH minus. That's another way to write the reduction at the cathode. At the end of the day, in both answers, we obtained H2 gas. Okay, now moving on. Use the diagram below to answer the questions. Electrolysis of molten. So in molten, we don't have to think about ions of water. So at the cathode, the K plus ions are discharged because the cathode is the negative electrode, so K plus will be attracted to it. And at the anode, I have, which is positive electrode, I have the Cl minus ions discharged, ready to do oxidation. So at the anode, it's Cl minus being oxidized into Cl2. So at the anode, that's, write the reaction. This must be written down in here. So at the anode, it is Cl minus giving Cl2 gas. Now, when you are writing the equation, this is molten. So Cl minus is in the liquid state. And at the cathode, it is the X plus, the K plus molten that's going to give me the metal through the reduction. And potassium here is going to be liquid. So at the anode, I have Cl2 gas, and at the cathode, I have molten potassium. Write the overall equation. Now, 2 electron, 1 electron, we multiply this by 2. The overall equation, 2Cl negative, be careful to the physical states, 2K plus molten, this is a molten ionic compound, Cl2 gas, and 2K metal, still molten since the temperature is very high. What are the products formed at the cathode and anode, respectively, during the electrolysis of molten magnesium fluoride? Again, when we say cathode, we think about Mg. When we say anode, we think about F. So at the cathode, I have magnesium metal molten obtained, and at the anode, I have fluorine gas obtained. Again, moving on, write Faraday's law to determine the mass or volume of the product produced at the anode or cathode in an electrolytic cell. Here, rest assured in the formula sheet, the formula are given to you. So, the volume of a gas, I'm just going to give the formula, is equal to the current multiplied by time. Here the time must be in seconds, divided by Faraday constant, multiplied by the molar volume, which is depending on RTP or STP, divided by N, which is the number of moles of electrons lost or gained per a mole of gas. I'm going to mention this now. Or if they are, so this is the molar volume. So VM could be 22.4 liter or 24 liter, depending if it's STP or RTP. Now, if we're dealing with a metal, in this case, not a gas, so there's another formula, which is the mass of the metal obtained at the anode or cathode, equal to I, again, current times the time divided by Faraday. And here, instead of saying molar volume over mole, we're going to say molar mass over mole of electrons per mole of metal or gas. So that's the formula. Let's take the first example. An electrolytic cell is used to electrolyze water using an inert platinum electrode. A current of 2.5 A. So again, I'm just going to write the formulas here on the screen so that you can still see them. I and T, Faraday, molar mass, and mole. So now I have the current, that's I. Passed through a cell for 30 minutes, that's the time. The time T must always be in seconds. So how do I go from minute to seconds? I multiply by 60. So that's in seconds. Calculate the volume. So we're not dealing with this formula. So we have to use this formula. The volume of hydrogen. Oh my God. My bad, I wrote M instead of writing V. So we need to find the volume of this hydrogen gas produced at standard temperature. So they told us that it is at STP. So now I know which volume to use. The molar volume over here is going to be 22.4 liter per mole. Temperature and pressure at the cathode. Now, since we're dealing with hydrogen at the cathode, so at the cathode, H plus is changed into, it is reduced into hydrogen gas, and therefore 2 electrons are transferred. So this one is equal to 2. So N in the formula, 2 moles of electrons per 1 mole of hydrogen obtained. So every 1 mole of hydrogen obtained requires 2 moles of electrons to be gained. Let's substitute in the formula. Volume is equal the current, I'm here, multiplied by the time, divided by Faraday constant, which is 9. Wait, let me get you the value. Faraday constant is equal to 96485 coulomb per mole. This value is always given, multiplied by the molar volume, STP, so it's going to be 22.4, divided by moles of electrons. Plugging this into your calculator, you will get 0.522 liters. That's the answer. Common particles and their symbols used in descriptions of radioactive decay and nuclear transformations. Let's first begin by listing these particles and finding their symbol. So here, 1 second. Okay, here's the pen. So the particles that we need to know: alpha particle, it's alpha, or He, that's the alpha. I can do it as alpha like this. 4 is the mass number and 2 the atomic number. We also have the beta, which is that's the symbol of beta. So in the beta you can either write like that, or beta minus, or simply E minus the electron. 0 minus 1 is 0 minus 1, so it's a negative. It has a 0 molar mass, molar mass number, sorry, and the atomic number is -1 with a negative charge. Another example, gamma rays. So gamma, that's the symbol of gamma, 0 and 0. We also have the positron. The positron, it's a positive particle, so it is beta, but instead of negative, it's a beta positive, and here it would be +1, or you can simply write Ce plus 1, like that, E proton, I mean the positron. Electron capture, so alpha, beta, gamma. Let me mention the neutron. The neutron, it is N symbol, 1, 0. What else? I hope I'm not missing anything. So these are basically the charges, the particles, the radioactive particles that are coming on my mind. Now, complete the table. If I have an alpha emission, what would be the change in the atomic number? When we say atomic number, we're talking about here. So if an alpha particle is submitted, whatever substance emitted in this case, it's going to be 2 digits less than the parent. So this is the daughter nucleide, and that's the parent. So whatever daughter nucleide we get, it's going to have an atomic number with 2 numbers less. So the change is 2 numbers below, and the change in mass number, whenever we talk about mass number, it's here, because the particle emitted has 4 mass numbers, so it will decrease by 4. Emission. Look at the particle beta. It has 0 mass number, so there is no change in the mass number. However, the beta particle has a -1 atomic mass. So, atomic number. Therefore, the daughter nucleide obtained is going to be 1 number higher than the parent. So, the atomic number is going to increase by 1. Why I'm saying this? Because the mass, the numbers should be conserved. And when you look at it, whatever mass, atomic number, Z plus 1, -1, it's going to be equal to Z, so it must be conserved, and the mass number also must be conserved. So A plus 0 is equal to A, whereas here A minus 4 plus 4 is still equal to A. So we have to do the balance in order to keep the parent nucleide mass number and atomic number equal to the mass number and atomic number in the product side. Positron emission, again here 0, so no change in the mass number. Whereas in the atomic number, since here there's a +1, so there's a decrease by 1. Now, in the electron capture, mass number is not changed, but the atomic number of the daughter nucleide, see, Z minus 1, so it must be less by 1, so -1. When you do the equations, you will practice this, you will find it super easy. Which of the following correctly describes an alpha decay? Alpha decay, it means we obtain alpha. with the daughter nuclide. So here it's going to be -4 and here it's going to be -2. And that's the parent. Okay, a nucleus emits an electron. No. A neutron transforms into a proton. No. A helium nucleus is emitted from an unstable nucleus. Moving on. Write a nuclear equation for the formation of thallium. Well, that's too large. Formation of thallium from uranium. You have your periodic table. The question says thallium is formed from uranium. So uranium is a parent nuclide, thallium is the daughter nuclide. Now, whatever number they give you, this is the mass number. Because the atomic number Z, you can get it from the periodic table. It doesn't change. It's constant. It's unique for every atom from periodic table. So 238 and this is 234. Now I'm going to use my periodic table and I'm going to find out what is 234. What is the atomic number of uranium? It is 92 and the atomic number of thallium is 90. Now it says here, look at this one. 234 and this is 238. So what is missing over here? 4 is missing because 234 plus 4 equal 238. And 90 plus what is 92? 90 plus 2. 4 and 2, these are the mass number and atomic number of alpha. Radon 222, that's radon or N222, radon atomic number is 86, undergoes alpha decay, so it's gonna emit alpha. What is the resulting nuclei? 222 and then -4, so it's gonna be 218. Because I wanna make sure that 218 plus 4 still gives me the same number. And 84 plus 2 gives me 86. So that's an X. Going to the periodic table, you look for what is the element having 84 atomic number. That's polonium. So here's the answer. Define the half-life of a nuclear reaction. The half-life is the time required for the initial amount, the time taken by the initial amount or quantity of the radioactive substance of the substance to decrease to its half. So for example, if I have 100 grams of a radioactive substance, I need to check how much time is taking for the 100 to become 50 grams, half of the quantity. So this is the time required for a half of a sample of a particular radioisotope to decay and reach half of its original amount. Identify the order of kinetics for nuclear reactions. All nuclear reactions follow the first order kinetics. In your formula sheets, you have these formulas. T half equal 0.693 over K, and you have ln. The first order, I'll just tell you, it's the second one given in your formula sheet, because the first one is 0 order, so the second one, that's the first order in the integrated laws, minus KT. Okay, so be careful to this formula. So the first one given in your formula sheet is for 0 order, the second one is for first, the third one is for second order. Now let's move on with the questions. A radioactive isotope has a half-life of 3.8 days. So I know that T half is 3.8 days. If 0.57 grams remains, so this is the mass of A at a time T, not initial. 57 grams after a time of 5.5 days. What is the initial mass of the isotope? I can simply apply the formula of half-life, which I wrote it over here. Okay, so in this case, I'm gonna say ln of 0.57 at a time t minus ln initial, which is I'm gonna find, equals minus k times t. Now we're talking about 5.5 days. I still need to find k, so I'm gonna use the formula t half. This one equals 0.693 over k. Now instead of the t half, I'm gonna substitute with the 3.8. Therefore, plugging this into your calculator, 0.69 over 3.8, the k is equal to 0.182, so I'm gonna put it over here. Solving for x, I can find the mass to be equal to 1.55 grams. However, I have an easier formula for you to use, which is the remaining amount equal the initial amount multiplied by half raised to the power n. N is how many half-lives we have. So here, n is going to be the time, which is 5.5 days, over the half-life, which is 3.8. So by dividing 5.5 over 3.8, that's a 1.447 half-lives. So 0.57 equal A initial times half to the power of 1.447, and it's the same answer. Choose the way that you like. Moving on. Complete the following table. This one, basically, it's completed. Alkane, that's the general formula. Alkene, it's having a double bond. Alkyne, that's the general formula with a triple bond. Let's move on to the hybridization and geometry. We are only interested in the hybridization of hydrocarbons. So we're going to discuss carbon of alkane, carbon of alkene, and carbon of alkynes. So if I have an alkane, around the C, all the bonds are single. So around the C, I have 4 domains. So the geometry is, the hybridization is sp3, and there are no lone pairs in all the hydrocarbons. So don't worry about the hidden electrons. And this one is tetrahedral, having 4 domains. For alkene, I have 1 double bond and 2 single. So we are dealing with 3 domains. And in this case, the hybridization is sp2, and the geometry is trigonal planar. You just have to locate the carbon you are asked about and count how many domains around that carbon. In the alkynes, we have 2 domains. 2 domains means sp, and the shape is going to be linear. Now, in case you are asked about the angle, in the tetrahedral, it's 109.5 degrees. In the trigonal planar, 120. In the linear is 180 degrees. Isomers. Which structure is not an isomer? So it means that in this question, 3 of them are isomers, having the same molecular formula of this one, but it's simply not the same compound. So first of all, let's count. 2, 3, 4, 5. That's a C5, and H, I have 2, 4, 6, 12. Okay, now looking at this one, That's not an isomer. That's identical. 1, 2, 3, 4. Oh, wait. That's nothing. That's different. 1, 2, 3, 4, 5. That's different. 5. That's 5 carbons. Okay. Still straight chain, no branches. That's not an isomer. H12. Let's look at this one. This one, 1, 2, 3, 4. So the main chain is 4 carbons with a branch. That's an isomer. And this one, 1, 2, 3, 4, 5. That's also an isomer with a 3 main chain and 2 branches. So A is not the isomer. Moving on, identify the type of isomers below. So here's 4 straight carbons, 3 straight with 1 branch. So these are isomers where their structure is changed. So we call them structural isomers. Which of the following compound can be cis and trans isomer? Can have geometric. To talk about geometric isomers, we need to have a double bond, a presence of a double bond in the middle of the carbon chain. And you cannot tell me one butene and tell me this one butene has isomers cis and trans. Why? Because the double bond is at the beginning of the, so I have hydrogen here, 1, 2, 3, and 4. So that's not, I can't have a double bond. Okay, let me fix my handwriting. So the presence of a double bond, it has to be in the middle of the carbon chain, not on the sides. And it doesn't work with triple bond, only double bonds. So single bond, triple bond, I'm left with ethene and butene. Ethene, 2 carbons. So all the hydrogens surrounding the double bond, all the groups surrounding the double bonds are the same. So it cannot have cis and trans. Whereas in the butene, I'm gonna draw it over here. Butenes means 4 carbons. 4 carbons, and the double bond is on the second. So that's carbon number 2, means there's 1 before, 1, 2, 3, and there's 1 after, 4. So I'm gonna fill it with hydrogens. That's cis. And when I put this CH3 and H, flip them like that, that's a trans. So the answer is 2-butene. And here we go. Here's the formula we're talking about. 1, 2, 3, 4. That's trans 2-butene. And that's cis. Oops. That's cis 2-butene. Now, what are the prefixes? And explain. Okay, in the cis, the large groups must be facing each other around the double bond, or the small groups must be on one side of the double bond. Whereas in the trans, the large groups must be oppositely to each other, not on the same sides of the double bond. You can either say large molecules, or you can discuss the hydrogens, see where they are. What are the prefixes used in naming organic compound? I advise you to memorize this table, as it's not going to be given to you in the exam. So here we go. First, we choose the main chain, and I have a branch on it, and I'll start counting from the side closer to the branch. 1, 2, 3, 4, 5, and 6. Place the number inside the carbons so that you don't miss anything. 6 is a hex. Now, since this is an alkane, it's going to be hexane. And on the second carbon, I have a branch made up of 1 carbon, so it's a meth. Now, since this is a branch, I'll use the termination methyl. Again, another example. This is the main chain, and these are the branches. So 1, 2, 3. So I have a prop, and it's ane because it's an alkane. Now on this propane, on the second carbon, I have 2 branches, so you must write the 2 numbers even if it's the same number repeated. And each group is a methyl group made up of 1 carbon. So instead of writing methyl, you are going to write dimethyl. Of course, the termination YL because these are branches. Again, there are no branches in this one. 1, 2, 3, 4, 5, 6, and 7. That's a heptane. Next, 3 hydrocarbons. Okay, that's a single bond. That's a double. That's a triple. Saturated because it's a single bond. Now the double bond and the triple bond are the unsaturated hydrocarbons. Keep that in mind. Now in case of electrons, here 6 electrons shared, 4 electrons shared, 2 electrons shared. Functional groups. You have to remember to memorize these functional groups. It's hard, but with practice you'll get used to them. A halocarbon is a compound containing an element of group 17, a halogen. So there's the carbon chain, and on it you might find a Cl or a Br or a F or an I. So the name of the functional group is called halogen, belonging to the formula of halides or halocarbons. Halides. Now, any group, any carbon chain, R is the carbon chain, containing OH functional group in it, means this belongs to the family of alcohols, and this functional group is called hydroxyl. Ether, that's a good thing. Ether, family name, compound type, and functional group the same, just like ester as well. They have the same name. However, ether is whenever I have an oxygen between carbons. So R again is a carbon chain. Now, whenever I have a nitrogen atom, this belongs to the family of amines, and it's an amino functional group. Now, carbonyls, we have 2 types, 2 groups of carbons, the aldehydes and the ketones. Both of them, there's a C double bond, so they have the functional group carbonyl. Now, what happens here is that the C double bond O is the carbonyl group. In aldehyde, this C double bond O is surrounded from one side with carbons and other side with hydrogens. Remember, aldehyde, letter H, which reminds me that there's a hydrogen next to the C double bond O. Whereas the ketone, they're all carbons. It's C double bond O in the chain. Carboxyl, it means there's a hydroxyl and a carbonyl together. There's a carbonyl and a hydroxyl groups together on the carbon chain, and this belongs to the family of carboxylic acids. Ester, it's a C double bond O, and then there's an O, and you continue the chain with carbons. So that's the functional group. Amides, it's a C double bond O with an amino after it. C double bond O, and then there's amine, nitrogen. And here continues the hydrogen. Now this nitrogen could be bonded to hydrogens or could be bonded to other carbon chains. So amide. Write the type of the compound. So let's go and see. Here's the functional group. That's a hydroxyl functional group. Name the functional group and write the family. So I'm going to do them again together. Hydroxyl belongs to the family of alcohols. O in the middle of carbons, that's an ether belonging to the family of ethers. That's the functional group. Whenever you see nitrogen atom and no double bond, that's an amine, and That's an amino, the functional group belonging to the family of amines. Now carbonyl, C double bond O, that's a carbonyl. If there's a hydrogen next to it, so carbonyl and carbonyl. However, if there's a hydrogen, that reminds me with the aldehyde. And only carbon, that reminds me with the family of ketones. Now, a carbonyl and a hydroxyl group, that's the carboxyl belonging to the family of carboxylic acids. Again, ester belonging to the family of ester. And I have here a C double bond O, and this double bond O is connected to a nitrogen. That means I have an amide, and the functional group as well is called amide, like in the proteins and the peptides, these things. Moving on with the questions. Calculate the absorbance of a solution with concentration, absorptivity, A, and B, the size of the cuvette. In your formula sheet, there's a formula written about Beer's law, and it's in the first, wait, let me check. It's in the first page, in the section of gases, liquids, and solutions. It's written A equal molar absorptivity, epsilon, okay, multiplied by B, which is the path length of the cuvette, where the light is going to go, multiplied by the concentration. So remember, these values are also given in the table next to the formula sheet, indicating what each one means. So the molar absorptivity is 200. The length of the light, the cuvette, is 1 centimeter. Okay, and now see centimeter, so you don't have to worry about converting units, and 0.15. So the answer is A, no unit for absorbance. What are the factors included in Beer's law expression for determining how much light passes through a liquid? So here's the cuvette. The light has to pass, and the liquid usually is colored. So it's gonna absorb some of this light, and the rest of this light, after whatever is absorbed, is gonna continue and it will be transmitted. So here we measure the absorbance. Now, of course, the color of the light is important. The color of the solution is important. So, which indicates the molar absorptivity. So, it affects how much light will be absorbed by this solution. Now, the size of the cuvette, whether the cuvette is 1 centimeter or 2 centimeter, it's going to affect how much light is going to be absorbed throughout its path. So it's very important to use a known size of a cuvette. C is the concentration. So based on the concentration, we can know the absorbance. More concentration, more absorbance. Less concentration, less absorbance. A student measures the absorbance of different concentrations solutions. So as you can see here, the datas are increasing. So he's checking it at different concentrations, and here they are. Of course, it's a linear relationship because they are directly proportional. So what is the absorbance at, what is the concentration at this absorbance? So we're basically dealing here. This is 0.25, and probably this is 0.273. So the absorbance is almost 0.05 molar. Moving on with the next subtopic. Why boron is used in glass manufacturing. So boron is a kind of like a semi-metal. You need to, this is a part where you have to memorize. Okay, so it's a metalloid. It has a small size, and it is used in glass manufacturing, the Pyrex, which is known because it reduces the expansion of glass when heated. It can hold on high temperatures, so it makes it a good candidate for glass, as a glass manufacturing. Okay, it is more stable. It forms a network, so it doesn't expand a lot. It can reduce the expansion of the glass when the glass is heated. So for all these reasons, we use boron in the glass manufacturing. Differentiate between graphite and diamond. You have to know that in diamond, the carbon is bonded to having 4 atoms bonded to it, whereas in the graphite, it's having 3 bonds, which means that there's 1 electron free. And this electron free is the one that's going to be responsible for the conduction of electricity. Diamond, they are not good conductors of electricity, and they're hard, they're rigid. Basically, they're used as cutting materials. Graphite, since there are 3 bonds connecting the carbons together, so they're not that hard. They're soft and greasy. It's made up of thin sheet, like layers of carbons on top of each other. So, and these layers are sliding over each other, and they're hanging together with intermolecular forces, like London dispersion forces. So they're not that hard. Moving on. Identify some properties of nitrogen and phosphorus. Again, this is a part where you have to memorize nitrogen and phosphorus. So first, let's begin. This belongs to group 15, period 2, and this belongs to group 15, period 3. Now, nitrogen atomic number is 7, phosphorus atomic number is 15. Of course, phosphorus is larger than nitrogen if I want to look at the properties. Now, nitrogen can form diatomic molecules, whereas phosphorus, it doesn't form diatomic molecules. So that's one of the differences. If I draw the Lewis structure of nitrogen, it can make triple bond with 2 free electrons. And phosphorus, there is no Lewis structure to draw here because phosphorus will not form a diatomic molecule. However, phosphorus has different allotropes. The allotropes of phosphorus, you don't have to memorize them, but there's one like P8, well known. So that's an allotrope of phosphorus. It has different allotropes. Okay? Nitrogen is gas at room temperature, phosphorus is solid. Just think about comparing these two. If I want to write the electron configuration of nitrogen, it is 1s2, 2s2, 2p3. Whereas in the phosphorus, it is 1s2, 2s2, 2p6, 3s2, 3p3. That's it. Okay? Predict the properties of elemental sulfur. Which element is extracted from ground in the elemental form? It is the sulfur. The rest are found combined with other compounds. Describe the properties of elemental oxygen. Elemental oxygen, we're talking about O2 and we're talking about O3. That's the elemental oxygen. The oxidation number of oxygen in the elemental form is always 0. So, in this one, okay, that's a diatomic molecule. That's a triatomic molecule, molecular formula O2, molecular formula O3. Oxygen in general, in both of them, it has 8 as an atomic number, and the configuration is 1s2, 2s2, 2p4. It has a molar mass of 32. And 48, so here 48 gram per mole. This one is 32 gram per mole. You can think about that. Now, in both cases, it's a colorless gas, odorless gas, and it's a gas at room temperature. Okay, so gas, colorless, and odorless. Basically, these are common. Now, uses of ozone. You can find ozone in the upper layer of the atmosphere, and it's the one that is going to protect us from the UV light coming from the sun. So it absorbs these UV light and doesn't let these light come to us. Now, oxygen Lewis structure is O with double bond O with 2 lone pairs on each O, whereas ozone, it has resonance structures. So, like that, the double bond can rotate between these 3 atoms, and it can move from here till here. So, this is the other resonance structure of oxygen, of ozone. Moving on, explain how oxygen is extracted from the air. How do we extract oxygen from the air? So to separate the oxygen from the air, we use fractionation. So by fractionation. So what happens is that the air is liquefied, the air is gas, so we make it into liquid. It is liquefied, it is cooled until it becomes liquid, then it is warmed again. So then again to turn into gas. So cooled and then warmed. At that point, all the other gases will vaporize before the oxygen. So the oxygen is the last one to become gas, and like that we can collect it. List the properties of halogens. Halogens are the elements of a group 17. They form diatomic molecules F2, Cl2, Br2, I2. F2 is known as the most electronegative atom of the periodic table. So they are all electronegative, but F has the, so if I'm comparing atoms, okay, so I don't want to get you confused between the diatomic molecules. The diatomic molecules, we do not discuss electronegativity in them. We discuss the electronegativity of atoms. So F has the highest electronegativity in the periodic table. Now, as I go down the group, the size of the atomic radius increases. And as I go down, the electronegativity, as I go up, the electronegativity increases. They all have 7 valence electrons, 2 electrons in the s and 5 electrons in the p orbitals. And most of them, their oxidation state in ionic compounds, the oxidation state of FCl, Br, and I in ionic compounds is -1. However, in other compounds, F is always -1, but Cl, Br, and I could change. When they combine 2 metals, they form ionic compounds, and they can also combine 2 non-metals, like for example, ClO2 minus. So Cl is combining to a non-metal. In this case, the oxidation number of Cl is not -1. Whereas F, whenever it combines 2 non-metals, it is always -1 without any exception. In this case here, O is +2. Here Cl is not -1, it is plus 3. Moving on, differentiate using examples between substitutional alloy and interstitial alloys. Now, you need to know that if I have an alloy, it's a combination of, the metals are next to each other. Okay, that's the structure of a metal. However, in the substitutional alloy, some of the metals are replaced with metals of the same size. So, it's atoms of comparable radius that substitute one another in the lattice of the metallic structure. A good example of substitutional alloy is the brass, which is made up of carbon and zinc. What else? Substitutional alloys. Here, substitutional alloys are less malleable and ductile than the pure metal. They're not more malleable, they're less malleable, less ductile, and the density, it's between, the density is the average density of the metals forming this alloy. For the interstitial alloy, it's basically a bit different than substitutional alloy. So I'm gonna erase what here, and I'm gonna tell you that this is the metal lattice, and another metal is filling up the holes between the metals of the lattice. So it's basically metal mixed with elements of smaller size, like hydrogen, boron, nitrogen, or carbon. So this will retain the metallic properties. So hydrogen, boron, nitrogen, and carbon could be filling the holes in interstitial alloy. Okay, and an example of interstitial alloy could be steel. Yeah, so could be steel. I don't think you need to know some examples, but anyway, I'm telling you because it's mixed of iron and carbon, so this is a good example of interstitial alloy. Moving on, properties. Complete the table. Here we need to talk about the properties of metals and their uses. So, titanium, low density. God be with you in memorizing these. Titanium is used in hip surgeries, so definitely it resists corrosion. So it has a low density, it's not heavy, so it makes it a perfect metal to in bones, to placed in body for injured people. So corrosion resistant, it doesn't corrode. And also because it's light, it's used in aircraft engines, or you can mention in surgeries. Chromium, that's Cr, it's hard, it's like crystals, it breaks easily, brittle, and we can find it in stainless steel and electroplating. It's well used in electroplating because it has a very nice color, shiny silver. Cobalt, it's a hard metal, it's magnetic. Cobalt, nickel, and iron are all magnetic. So magnetic, and it can resist corrosion at high temperature. Resist corrosion. Cobalt is used in batteries. Iron is very strong. We use it in constructions for buildings. So in constructions, it corrodes. That's why it must be mixed. So nickel can be also magnetized, and it's a corrosion resistant. It doesn't corrode easily. So corrosion resistant, as I said, magnetic. and we use it usually in coins and mixed with metals to form alloys. Copper, the best conductor. It's a good conductor, it's malleable, it has a red-brown color, it's used in wires for electrical conductivity. Electrical conductivity. Zinc, lustrous. Lustrous means shiny. It's like a mirror. If you put it in front of you, you can see yourself. Lustrous. And it can used as in galvanization as the word are escaping. It's like a sacrificed electrode as a to protect whatever metal that we want to protect from corrosion. So galvanizing steel. So it can protect steel from corrosion. Now, whenever you get a question to identify properties of transition metal, in the exam, they're probably going to ask you to list 2 or 3 properties. So just think about any metal in your mind and say that they are shiny and they are malleable, ductile. List the properties of metals. Conduct electricity, solid at room temperature, except definitely mercury, solid at room temperature. Most of them, they have silvery to grayish color, except gold and copper, of course. They have similar properties. They have, because you said solid at room temperature, so they have a high melting and boiling point. So they form positive ions by losing electrons. So anything that can come to your mind, you can put it as a property. They have high density, some moderates. Some are hard, some are not that hard, some are not strong. So, and their valence electrons are in the d orbitals. Describe their oxidation states. They have many oxidation states, like for example, copper, 2 oxidation states and others. And that's why they are colored ions. Now, the last part that you need to know is the complex ion. That's an ion, that's a compound. So I don't see a charge over here because it's a compound. Now, how do we deal with this? A complex or coordination compound is a compound made up of a transition metal linked to several ligands. The ligands could be charged, could be neutral, and there is next to it, after or before, a counter ion. Now, the counter ion will be written after, so it's written after the complex ion, so the whole thing is a complex ion if the complex ion is positive. Now, if the complex ion is negative, so I'm going to give you maybe another example, like K3FeCN6. If the complex ion is negative, then the counter ion is placed before. Now, complex ion, here it is CrCO6. Now, from where do I get the charge of the complex ion? I can get it from the charge of the counter ion. Now, since here we have a 3 Br, and what's the charge of Br? It's -1. So the total charge is 3 negative. Therefore, my complex ion is 3 positive. The ligand is CO, and we know that CO is neutral. Now, differentiate among ligands, coordination, ions, coordination compounds. I'm going to give you the list of ligands that you need to remember. Water. These are compounds that can be either charged or neutral but having free lone pairs on it. And NH3 with a lone pair, and CO with a lone pair. However, you have charged ligands like chloride ion, cyanide ion, thiocyanate ion, SCN minus, and oxalate, C2O4 2 minus. Okay? Now, ligand plus transition metals form a complex ion. So, complex ion is when the ligand combine with the monoatomic ion, which is the metal. And usually it's more than one ligand they combine together. So I'm going to give you some examples over here, like FeCN6. How do I know the charge? I look at the charge of K. K is positive 1 and I have 3 of it. So total 3 plus. So this one is going to be 3 minus. That's a complex ion. Or CO6, that's a complex, another complex ion. They are combined together. And what else I should say? Coordinate compound is when I put the complex ion and the ligand and the counter ion together to make a complete compound. Okay, so make sure that the total charge of the metal and the ligand is equal, or like it's neutralized by the charge of the counter ion. What is the oxidation state of iron in this complex ion? Here, this is a ligand, we have 6 of it. And this is Fe, the ion, the whole thing is a complex ion. Now, what is the charge of Fe in this one? Now, this ligand is -1. We have 6 of it. You see, we have 6 of this ligand. That is a -6. Now, Fe, I still don't know it, so I'm going to name it as X. And I'm going to have -6 ligands equal. The charge of this complex ion is -3. Therefore, the iron has +3 charge. Good luck in your exam and thank you.